So I was given the task to be the first speaker and survey some of the materials challenges in batteries. And what I'll try and do in 10 minutes is go from the very simple descriptions of what a battery is to where we're going and what the challenges are. But I just want to sort of remind everybody, given it's the first talk of the session, of why are we doing this, why our batteries are important. And of course it's the two things: it's reducing CO2 emissions, reducing pollution, but also thinking about trying to do this in a way that's sustainable for our planet. So just reflecting a little bit more on why is this important. The Faraday Institution, of course, is focusing on the automotive sector, but one of the bigger challenges we also need to think about is how we make an impact on storage on the grid. So as we're increasingly using more and more renewables, the grid becomes increasingly more unstable, and we need to be able to do this. And I think one of the biggest challenges we have is to take one of our little batteries, which essentially have a format of this size at the individual cell level, and expand it so that it becomes a battery the size of this room. And you can't just do that by making a fatter and thicker battery, because the ions can't move fast enough. And of course we've got a long way to go. So just to sort of set the CO2 issue in context, the challenge we have from a perspective from the automotive sector is that we need batteries that can respond very fast, be it being regenerative braking in a hybrid system, through to giving the energy density that we need for an all-electric vehicle, and to do that in a way that's cost-effective for a larger fraction of the community. So what is a battery? So this is a slide that essentially tells you why the Nobel Prize was won, with John Goodenough's lithium cobalt oxide and the graphitic anode from Yukiro Yoshino's work put together. But why I'm putting it there is not to remind you that we have lithium cobalt oxide and graphite in the your batteries that are sitting in your laptops and your mobile phones, but to remind you that this is a very complex system. So we'll take an active material, but we need to put it together with a binder to hold everything together as you pull the lithium in and out and the materials expand and contract. And then a carbon black, which acts as a way of getting the electrons in and out. And so you pull the lithiums out, they go through a non-aqueous electrolyte, and then nominally safely intercalated or inside a graphitic anode. And this material operates under non-equilibrium environments. And so when you fully lithiated the anode and you fully deintercalated or oxidized the lithium cobalt oxide, those materials are metastable. In other words, if you heat them up, this material gives off oxygen, and the material decomposes, and it only survives because you formed a passivating layer on the anode called the SEI. And so a lot of work has gone in, from taking the original discoveries of John and Stan and Yoshino through to getting the material that now cycles for many, many charge and discharge cycles in our portable devices. Now the challenge is, how do we make it cheaper and last for the 7 years for electric vehicles and the 20 to 40 years that we need for the grid? So to put this in context, you also have to remember that since the lithium-ion battery was invented more than 25 years ago, its energy density has gone up, and it's gone up from new materials, better engineering, putting more stuff into the same volume, and its price has gone down by more than a factor of 10, but we are reaching close to the theoretical limits. New approaches are needed. So we can't just go on projecting increased energy densities of batteries without coming up with new chemistries. And we can't think about putting the same amount of material into a same volume without safety issues. So what are the challenges? So just to sort of reflect briefly on why batteries fail. I mentioned the idea that the electrolyte is metastable when it's charged, and you form this passivating layer that's required, that has to be stable. If you heat your battery up, if you use it on your laptop, this material will start to decompose and your battery will degrade. And then we've got cost, we've got materials, resources issues, and we've got capacity challenges. So if you take a lithium cobalt oxide system, you can only pull out about 50 to 60% of the lithium before it becomes too unstable and you can't get reversibility. So there's a lot of chemistry to be done. So moving away to think about how electric vehicles work, we move from lithium cobalt oxide, which is expensive, is often mined in places in the world with environmental consequences, and we moved to lithium nickel oxide. So lithium nickel oxide is cheaper, it allows higher rates, but it's unstable. And so what we've done over the years is to increase stability by adding aluminium, but that then comes at a decrease in the capacity. Then moving to materials like NMCs, we can up the capacity again, but then we're back to adding cobalt and adding more cost. And so what we're doing now is to try and move to materials that have as much nickel as we can have as possible, so moving to materials such as, sorry, I can't move my mouse and not press the advance button at the same time. Materials such as 811 with 80% nickel, 10% cobalt and 10% manganese, which is a good compromise in terms of cobalt use, but it's more unstable as you're putting more and more nickel into the system. And so one of the challenges of the project that I lead within the Faraday Institution is to figure out how it degrades and come up with solutions to mitigate that, and then move forward to materials with increasingly more nickel and less cobalt. So what about the anode side? We can move to things like silicon. So silicon can combine with more lithium ions per unit silicon to give you a higher energy density. So you can take 4 lithiums and react with 1 silicon to make an Li4Si, as opposed to lithium that reacts with 6 carbons to make LiC6. So you get 10 times the energy density. But you do that at the expense of a material that expands and contracts as the lithiums go in. And what that does is cause problems with the battery, because you don't want a battery that sort of doubles in size all the time. But really that's not the biggest challenge. The biggest challenge is it exposes fresh surfaces that react. And so while car manufacturers are putting small amount of silicons in the battery, they're having to struggle to try and solve these degradation issues. So we can reflect on ways to reduce cost. So we can try and make cheaper materials, and we can do things like making thicker electrodes. So the more thicker your electrodes, the less of the other stuff that you have to have in them. We could have less of the separator that separates the anode and the cathode. We could reduce the amount of the expensive copper current collector and the packaging, but it comes with a challenge. So if you want to move an ion through a thicker material, it takes longer, and so you won't get the same power out of the system. So we need to design ways of arranging particles in a material that are still just as dense, but maximize transport. And so that's an active area of research. And then importantly, and this is the sort of area that I'm interested in, is trying to increase longevity. So we need to find the reactions that don't just cause degradation in the days and months, but might kick in year 7 or year 10 of a battery that's been designed for the grid. And that involves designing experiments in the lab that may only take the sort of timescales of typical PhD students or undergraduates or postdocs, which are months to years, to make predictions to move forward. And so that's something that we and others are trying to do, increasingly using sort of buzzwords like big data and AI to help us make predictions. And then, of course, we need to do this in a sustainable way and recognize that the actual production of a battery, whether it's the mining, whether it's the reduction of the metals to make the current collectors, or the heating to make the cathodes, has an inherent carbon footprint. So again, thinking about sustainability. So I don't want to spend very long touching on the reliabilities of shortages and reliabilities of source. I personally think we have enough lithium in the world. This is not the challenge. I think we have to reflect on the implications of where it comes from, and the security of supply, and also recycling. So in the end, we will recycle because we want the cobalt back and we want the other components back, and we'll do it because we have to do it globally. So this is just to say that the use of the lithium-ion batteries have been predicted to explode, no pun intended, and whatever metric or whatever's prediction you make, they've ramped up faster than most experts have predicted. So I just want to reflect on, in my last 3 minutes and 48 seconds, on some other things that the field is doing. So if you want to move, if you want step changes, we have to think radically, and that's why we need to be doing the research now in our labs in the UK and globally that are going to have the impact in the next 10, 20, 30, 40 years if we're going to meet the 2050 targets. And so you need to think about what are the more cheaper and more abundant materials. And so obviously on the cathode you can move to lithium to sodium, to magnesium, and on the anode we can increasingly think about using silicon and sulfur. And in principle these systems could give you higher energy density batteries, and I'd be happy to take questions more about what those challenges are. The other thing about sodium is that it allows you to move away from the use of copper as the current collector, but of course sodium is just that much bigger, so it comes with a penalty in terms of energy density. Magnesium is again a cheap element, but it has a 2+ charge, which means it's difficult to move, it's difficult to put out a solution. So the sort of ultimate battery is the lithium air battery, where you take lithium and you take oxygen from the air, so you have this free air floating around that you can use. And if you could get that to work, that has the same theoretical and practical energy density of gasoline. The challenge of it is that it has many of the challenges of a fuel cell and many of the challenges of a battery. You've got to take the lithium, you've got to take the oxygen, you've got to then react it at an interface and make a solid product that's insulating. And remember, our reactions work not only by lithium ions reacting with a material, we also have to get the electrons in and out. And so if this material is an insulator, that becomes a challenge. And so there's been a lot of progress, work by Peter Bruce, and work by my lab, for example, have looked at the use of redox mediators to allow you to oxidize and reduce this. And so this is one of the materials that we need to keep on thinking about working on, because it does represent the ultimate in battery technologies. And those of you who are chemical engineers in the audience will recognize the other challenge, which is that lithium also reacts with nitrogen, and how did you do an oxygen-nitrogen separation? So this was just going back to reflect on sodium-ion batteries. I've told you about the current collector issue. There were also issues on trying to get the anodes in the system. So I just wanted to touch on solid-state batteries for two seconds because of the press that they've received. So you can talk about solid-state batteries that are all solid-state, so all of ceramics, or you can also have ones that contain polymeric components, so they're sort of semi-solid state. I think one of the challenges is that with these systems, and I know that one of the speakers will talk about this later with more detail, is that if you have an all-ceramic system, this is a nice piece of work by a group in France where they've made pellets of ceramics, and in order for this thing to work, the lithium ions have to move backwards and forwards. And even if you're not a material scientist, you can see that it's very grained, and each of those grains has a boundary which is associated with resistance, and so these ions have to move backwards and forwards, and the material is expanding and contracting. And so that has to happen and has to work over multiple cycles. So I ultimately think that redox flow batteries play a role in the whole space. So this is the idea of taking a battery, but not having all the oxidized and reduced materials in the same box. So you're no longer constrained by that. You can have a vat of oxidized or reduced material, and when you want electricity, you flow them in and you get electrons out. So this sounds amazing. What's the challenge? The challenge is that we're still at the same sort of cost, and we need to find ways of getting more and more stuff into the vats. So I would just end by saying I think we need to think about the way the systems work at the atom level, through to the pack level, to the full-scale level, and that requires people like me. So there's not a science pitch for my own science. We do something very specific called nuclear magnetic resonance, where we look at the lithium ions to see what they get up to in situ, so while we cycle and charge and discharge our battery, which allows us to get some unique insights into how things function, but also how they failed. And so I will say that in the next 5 to 10 years, we're going to see combinations of new chemistries coupled with increased responsive BMS systems. I would like to imagine that we have increased sensors so we can follow on the fly what's happening, and then we can respond in real time and develop mitigation strategies. So thank you very much.